Good day and welcome back to the fourth and final part of our discussion of double integrals and polar coordinates. And as I mentioned in the end of the previous video, there is a worksheet related to double integrals which you could find posted in Canvas that hopefully you have already spent some time working through. If not, I recommend pausing this video, finding the worksheet, and spending a bit of time. You will certainly take much more out of that than just kind of passively listening to me. Not to mention the fact that it would probably be more interesting for you as well. So anyhow, problem number 1 on the worksheet. We are asked find the volume of the solid, bounded by the key word here, paraboloids, z equals 3x squared plus 3y squared, and z equals 4 minus x squared minus y squared. And I just want to mention, as I've kind of indicated previously, when it comes time for exams, part of the wording of the problem might include a statement along the lines of, to receive full credit, you must sketch the solid along with that corresponding region of integration for the double integral. And let me also note there was no reason we needed to include this word paraboloids. Those are equations of surfaces that hopefully, if not now, sometime in the near future, we will be able to quickly and efficiently recognize. So let's go ahead and sketch these paraboloids, and you can go about this using the method of traces, thinking maybe about x equals 0, y equals 0 traces, or if we just talk our way through this. Note, in either case, if the 3y squared or the 3x squared is not present, you would have a parabola opening up around that positive z-axis. And that's exactly what we have. So it's a paraboloid opening upward, having its vertex at the origin. So something of the shape given here. Then secondly, we have this surface z equals 4 minus x squared minus y squared. And from a similar kind of intuitive perspective, if the minus y squared or the minus x squared were not there, i.e. y equals 0 or x equals 0 trace respectively, you would have a parabola opening downward in the z direction whose vertex is at 4 on the z-axis. So roughly speaking, it's something that looks along these lines. And I'm not going to sketch the entire thing, as from the portion that I've sketched here, we can clearly see this bounded solid. For some reason, I'm thinking it looks like one of those plastic Easter eggs. Kind of you have the bottom half in red, the top half in blue. And I'm even going to go ahead and erase away some of these extraneous lines that we do not need. So we have our upper surface, in a sense, the z equals 4 minus x squared minus y squared. And then in red, we have this lower surface, z equals 3x squared plus 3y squared, where the 3's cause this to be a bit thinner, i.e. to grow a bit more quickly, whereas the blue paraboloid is going to be getting wider more quickly. Now, in order to set up our double integral representing the volume, we now have a perfectly good starting point. We could say the volume is the double integral over d, and in a sense, d is yet to be determined. And what we integrate is the upper surface minus the lower surface. So think 4 minus x squared minus y squared, the upper surface, minus the lower surface. And after this example, I may stop writing this, we will see. You think upper minus lower. That's our intuition. Now, in terms of determining what this region of integration D would be, what we want to think about, and I'll give you two perspectives. One is you can imagine there's a sun sitting directly above this z-axis, and what you want to know is what does the shadow of this solid look like. So you get a shadow down in the xy plane, which would correspond to D. An alternative way of thinking about this would be if you thought about just coming from the top and just squishing this thing down all the way into the z equals 0 plane. Similar to how you might stomp on a soda can to squish it down nice and flat. In either case, what you're going to end up with is what looks like a disk. And note, this disk that we see corresponds to the curve of intersection between the two solids. So the key observation we need to make is, what is the curve of intersection? Which we find by setting the two surfaces equal to each other. So when is 3x squared plus 3y squared equal to 4 minus x squared minus y squared? So we can add x squared and y squared to both sides. And we can also divide both sides by 4. So our curve of intersection would be a circle of radius 1 centered at the origin. And I find it easier to typically sketch a separate xy coordinate system. So our region D is made up on the outside a circle of radius 1 centered at the origin, which is once again something highly conducive to describe in polar coordinates. In polar coordinates, we can note the r values are between 0 and 1, and hopefully this is becoming quick and efficient. It's the entire circle, so our theta values are varying from 0 to 2 pi. And let's go ahead and evaluate our double integral. So before converting into polar coordinates, I'm going to simplify. We have a 4, and then if we combine the x squared terms, minus 4x squared minus 4y squared. And note, we are really subtracting away 4 x squared plus y squared. And whenever you are converting to polar coordinates, it is certainly in our best interest to think preemptively in terms of identifying x squared plus y squared, because we can immediately replace this with an r squared and hopefully save a little bit of algebraic simplification down the road. So the double integral, we have 4 minus 4r squared. The dA becomes r dr d theta. The r values vary from 0 to 1. The theta values from 0 to 2 pi. And once we get it to this point, you can distribute through the r, and then you will have a very reasonable integral remaining. And I will go ahead and write down the solution of 2 pi and leave it to you to finish the computations. But of course, along with the rest of the other solutions, you can find those details posted in the solutions to the worksheet on Canvas. And this completes our discussion of double integrals in polar coordinates. What remains for us is one more quick topic involving double integrals where we will investigate an application. So stay tuned and take care.